Deep learning has taken the world by storm, opening doors to unprecedented breakthroughs across various domains. However, these neural networks can be susceptible to a common pitfall, overfitting. And this occurs when a model becomes so intricately tailored to the training data that it fails to recognize well to the new unseen data. So here the regularization techniques are like a magical wand which helps to tame this beast and balance the model's complexity with its ability to generalize. This dropout is one such magical technique that has become a staple in the deep learning toolbox. It's like having a magical eraser for your neural network, randomly removing neurons and their connections during training. So, by doing so, dropout prevents your model from becoming too reliant on that specific neurons, reducing its overall complexity and guarding against overfitting. So in this video, we'll embark on a journey through this fascinating world of Dropout. We'll explore its theoretical foundations and practical applications and provide a hands-on tutorial to help you become a dropout wizard, mastering this powerful technique and casting it to vanquish overfitting from your deep learning endeavors. So let's get started with the regularization techniques. So in simple terms, regularization techniques are methods used to prevent overfitting in machine learning models. Overfitting occurs when a model is trained too well on that training data, memorizing its intricacies instead of learning the underlying patterns. As a result, the model performs well on the training data, but poorly on this unseen data, which leads to low generalization performance. So here this regularization technique helps to strike a balance between model complexity and generalization, which ensures that the model learns the underlying patterns and performs well on new unseen data. So here are two examples to help you understand this concept. First is the lasso regression. So this lasso regression is a type of linear regression that incorporates a regularization term in the model. And this technique adds a penalty to that model parameters, shrinking their magnitudes to avoid large values. And by doing so, lasso regression reduces the model's complexity, making it less prone to overfitting. So in layman terms, it's like wearing a corset that prevent your dress from being too tight, thereby avoiding the discomfort and potential damage to the fabric. Then comes the dropout. So this dropout is a regularization technique that randomly drops units or the neurons or connections in the neural network during training. This prevents the network from relying too heavily on a specific unit, forcing it to learn redundant representations and reducing the overall complexity. It's like having a game of operation with your neural network. And this game requires you to carefully remove parts without triggering the buzzer. Just as the dropout requires the network to function without specific neurons or connections. So in both examples, regularization techniques are used to strike a balance between model complexity and generalization performance, ensuring that model not only perform well on the training data but also on new unseen data. So let's explore dropout in detail now. So this dropout, it's a regularization technique which is used in deep learning models to prevent overfitting. And it works by randomly dropping or setting to zero a percentage of the neurons in a layer during training, effectively creating an ensemble of different networks. This helps the model learn from various versions of itself, which results in improved generalization and reduced overfitting. So to understand this better, imagine a complex recipe that has been passed down through generation. Over time, the recipe may have been modified slightly in different households, resulting in unique version of the same dish. So dropout also works in a similar way by creating variations of the neural network during training. This allows the model to learn from multiple versions of itself, which ultimately leads to better performance on unseen data. So in layman terms, dropout can be thought of as safeguard against overfitting. So by randomly disabling a portion of neurons, the model is forced to learn more robust features that are less dependent on any single neuron. This helps the model generalize better to new data. For example, consider a handwritten recognition model that has been trained on a large data set of handwriting digits. So without dropout, the model might become overly specialized to that specific handwriting of training data, leading to the poor performance on new unseen data. But when we apply dropout, the model is forced to learn more generalized features that can recognize handwriting patterns across a wide range of styles, resulting in improved performance on new data. Now, what about its methodology? So, this methodology involved in dropout is relatively simple but yet powerful. This idea was first introduced by Geoffrey Hinton and his colleagues in 2012 in a paper titled Improving Deep Neural Networks by Preventing Co-Adaptation of Feature Detectors. And the key steps which were involved in implementing the dropouts are as follows. First, define a dropout rate. The first step is to specify the dropout rate, which is the percentage of neurons that will be randomly dropped during each training iteration. And this rate is typically set as hyperparameter and usually a small value such as 0.2 or 0.5. The dropout rate controls the level of complexity reduction in model. Then, during each forward pass of training process, a binary mask is generated for each neuron in the layer, with the values being either 1, that is keep the neuron, or 0, that is drop the neuron. And this mask is generated randomly for each training iteration, creating a stochastic and diverse set of subnetworks. The dropout operation is applied element-wise to the output of layer, effectively setting the drop neuron outputs to 0. Then keep dropout inactive during inference. So it's important to note that dropout is only applied during training. During inference, the dropout masks are not generated and all neurons in the layer are active. This helps to maintain the integrity of the model's output during evaluation. Then train the model. Train this multiple subnetworks. So by randomly dropping neurons during each training iteration, the model is forced to learn more generalized representations as it cannot rely on a single neuron. This leads to an ensemble of different neural networks, each contributing to the final prediction. And finally, we update the model. So once that forward pass is complete, the model is updated using standard backward propagation algorithm to adjust the weights and biases. The dropout process is then repeated for the next training iteration with a new dropout mask being generated. So to summarize this all, we can say that dropout is a powerful regularization technique that helps prevent overfitting by reducing the complexity of models during training. And this randomized nature of dropout creates an ensemble of subnetworks which results in improved generalization and better performance on unseen data. So to understand its methodology better, let's calculate this dropout by hand. So this dropout is a simple yet effective way of reducing overfitting and improving generalization. So let's walk through its network architecture. It has a linear layer. It has then ReLU. ReLU means the negative values are converted to 0. Then we have taken dropout 0.5. Then we have again linear layer. Then we have ReLU. Negative values are converted to 0. So minus 4 will be 0. Then we have dropout 0.33. Then we have linear here. Now first we will do the training part. So we are given a training set of two examples, x1 and x2. Then random, that is p is greater than 0.5. So we will draw 4 random numbers. Okay, for each random number, if it is above 0.5, we keep it and denote it as 0. Otherwise, we drop and write it as cross here. Okay, so we have taken some numbers and this way we have done. So if it was above 0.5, so we have kept that number denoted as 0, and otherwise we have kept this one. Okay, so next dropout matrix, we will calculate the scaling factor here. The purpose is to drop the second and 4 nodes actually. So here we will drop the second and the 4 nodes and scale the remaining 2 nodes by 2. So that is why we have taken there 2 and rest is this much. Okay, so first we will do the matrix multiplication. We will multiply both these matrices and it will result in this. So for this we will use the popular formula, that is y is equals to wx plus b. W is the weight, X is your input matrix, B is your bias. So we will also use here the same formula. Okay. Yeah, and then we will check here the number of columns are 3, number of rows are 2. So this 3 4 will be multiplied by 1 0, adding 0 here will get 3 here. Then this 5 1 will multiply by 1 0, adding 0 here will get 5 here. So this way we will get. Now we will do the multiplications of both this matrices, will get the results like this. So here this negative value will be converted 0. So whenever you will multiply this, keep this 3 7 5 and 0 here. So 2 0 0 0, it will be multiplied by 3 7 5 0, it will give the 6 here. Then again we'll have the matrix multiplication of both these matrices will get here. So here if we check the number of columns 1 2 3 4 5, number of rows 4 here. So last one will be considered as a bias. So this 1 0 0 1 will be multiplied by 6 0 10 0, adding 0 here will get 6 here, right? So here negative value will be considered as 0. So whenever we'll do the next multiplication, we'll consider like this 1.500, here 6 10 and 0 will get 9 here, right? So here we have drawn 3 random numbers. Now this dropout. So for each random number, if it is greater than 0.33, we keep it and denote it as O, otherwise we drop and denote it as cross. So here we have taken 1.5 1.5 and cross here. Okay, so when we will do the multiplications of both these matrices, we'll get this, and finally we'll multiply these matrices, we'll get this. So here the number of columns are 4, number of rows are 3. So 1 minus 1 0 multiplied by 9 15 0, adding 0 here, we get this minus 6 here, right? Next we'll have this inferences here. So here also this is the unseen data, right? So that is we will have this matrix multiplication. So here the number of columns are 3, number of rows are 2. So 1 0 multiplied by 3 2, adding 0 here we get 3. Next we do the multiplications of both these matrices. So here we check the number of rows are 4, number of columns are also 4. So just do the element wise multiplication. But remember, as we are using ReLU here, the negative values will be converted to 0. So it shall be considered 3502, right? So when we will multiply both these matrices, we'll get this. In the next step, we'll multiply the elements of these matrices, we'll get this. So 3601 will be multiplied by 1011, adding 0 here, we'll get 4 here. Okay, so here though no negative value, so all are fine. In the next step, we'll multiply these matrices, we'll get the results like this. In the next step, we'll multiply these matrices, we'll get here. So here 494 will be multiplied by 110, adding 0 here, we'll get 13 here, right? Up to this we did. Now we have a feed forward network. So as we have all the matrices ready across the layers, perform the feed forward pass by calculating a series of matrix multiplications that we have done. Right, we have got the outputs here. Next we calculate the loss gradients of mean square error, and the formula is twice of y minus y dash. Okay, so first we will calculate the y, which we have calculated here. This is the y here, and then we'll have some y dash. Okay, so this is the y dash here. So first we will minus this one. So minus 6 minus plus 4. So minus 6 plus 4, that is minus 2 here. 9 minus 7, that shall be 2 here. Okay, so y minus y dash we have done, then we have twice it. So minus 2 into 2, that is minus 4, 2 into 2 4, 3 into 2 6, and this way. Okay, so we have done the things here like this. So finally we have this inferences, and then we have taken the forward pass to make the predictions about this unseen data. Now what are these limitations of dropout? So this dropout has proven to be a highly effective regularization technique for deep neural network, but it's not a silver bullet and has some limitations. So let's deal about it. First limitation is the computational overhead. So dropout adds an extra layer of complexity to the model as it requires generating dropout mask and adjusts the computations during training, which can increase the computational cost of training, especially when using larger models. Then hyperparameter tuning. So the dropout rate is crucial hyperparameter that needs to be carefully tuned for optimal performance. And this finding this right dropout for a specific problem requires experimentation and can be time consuming. Then inconsistent outputs. So during training, dropout randomly disables neurons, which can result in different outputs for the same input. And this inconsistency can sometimes lead to suboptimal convergence during backpropagation. So however, this issue is typically mitigated by the benefits of improved generalization. Next, not applicable to all models. So dropout is not suitable for all neural network architectures, especially those where the output of one layer directly affects another layer, such as recurrent neural network, convolutional neural networks with direct connections. So for these models, alternative regularization techniques such as recurrent dropout, convolutional dropout has been developed. Then no dropout during inference. So dropout is only applied during training and it is deactivated during inference. This can sometimes result in overfitting during inference, especially when using a low dropout rate. So to mitigate this issue, a variant of dropout called drop connect has been proposed, where connections are dropped instead of neurons, so allowing the model to retain its complexity during inference. So in summary, dropout is a powerful technique that has demonstrated significant improvements in many deep learning applications. However, it is essential to be aware of its limitation and choose an appropriate regularization strategy based on the specific problem and model architecture. Thank you.